So you want to go to space. Right now, there's only one way. Ride a rocket. Rockets are basically giant, controlled explosions. You sit atop a tank of flammable fuel, light the fuse, and hope everything works. It's spectacular, but also risky, like climbing a skyscraper with dynamite shoes. Rockets are incredibly complex. Millions of parts must work perfectly under extreme stress. One tiny failure, and it's a disaster. The energy needed is staggering. Thousands of gallons of fuel burn every second just to fight gravity. Every pound counts. More weight means more fuel, which means more weight. A vicious cycle. That's why sending anything to space is so expensive. Rockets are single-use, and the cost is astronomical. And let's not forget the danger. Astronauts ride a controlled explosion away from Earth, risking everything. It's a testament to human courage, but you have to wonder, isn't there a gentler way? We built elevators for buildings and bridges for rivers. Isn't it time for a calmer, more reliable way to space? Rockets work, but they're wild, expensive, and risky. Maybe it's time to dream bigger. What if we could ride to space without all the fire and fury? What does going to space actually mean? There's no line in the sky, but scientists use the Kármán line, 62 miles up, as the boundary. At that height, planes can't fly. You need a spacecraft, but just reaching space isn't enough. To stay there, you need to be in orbit. Orbit isn't just going up, it's going sideways incredibly fast. Imagine throwing a baseball so fast that as it falls, Earth curves away beneath it. That's orbit falling around the planet forever. The ISS orbits just 250 miles up, traveling at 17,500 miles per hour. Astronauts float because they're in constant freefall. If Earth were a globe, the ISS would be an inch above the surface, not far at all. But there's a much higher orbit, geostationary, 22,236 miles up. Satellites here orbit in sync with Earth's rotation, appearing to hover over one spot. This cosmic real estate is perfect for communications and weather satellites. It's also the key to one of humanity's wildest ideas, a space elevator. The top floor of our elevator would need to reach geostationary orbit. It's far, but its unique position makes it the perfect anchor in the sky. Imagine connecting Earth to this spot with a ribbon to the stars. That's the dream. Rockets are risky and expensive. What if we built a cosmic elevator instead? Picture a massive anchor on the equator, unspooling a super strong cable all the way up to geostationary orbit. A robotic climber would latch onto the cable and ascend. No explosions, just a smooth electric ride. The journey would take days, not minutes, but it would be safe, steady, and affordable. We could send cargo, satellites, and people for a fraction of today's cost. The space elevator would transform space from a dangerous frontier into a place you could commute to. It's a century-old dream, but could we actually build it? The answer starts with finding the right kind of cable. What material could stretch 22,000 miles into space? Steel won't work, it would snap under its own weight. We need something incredibly strong and light. For decades this was impossible. Then came carbon nanotubes, tiny tubes of carbon, 100 times stronger than steel, but much lighter. A thread of carbon nanotubes could support a car. Woven into a ribbon, it could be our elevator cable. It's the only material that could do the job, and it's real. But there's a catch. We can only make nanotubes a few inches long, not thousands of miles. Mass-producing a flawless continuous ribbon is a massive challenge. It's like knowing how to make a perfect brick, but not how to build a skyscraper. The basic ingredient exists, but the recipe for the final product is still a mystery. Solving this is the first step to building our elevator. Suppose we solve the cable problem. What next? You can't just hang a cable from space, it needs a counterweight beyond geostationary orbit to keep it taut. Ideas include capturing an asteroid or extending the cable even farther. Then there's space debris, even a tiny collision could sever the cable. We'd need ways to dodge or reinforce it. The ground station must be on the equator, in a calm, stable region. Building starts in space, a satellite lowers the first thread down, while a counterweight extends up. Once the thread reaches Earth, climbers add more ribbons, thickening the cable. It's a construction project unlike anything humanity has attempted. But if we solve these puzzles, the elevator could become real. The space elevator promises to make space accessible and affordable. Costs could drop from thousands to hundreds of dollars per pound. Space could open for science, industry, and maybe even tourism. But as of now, it's still science fiction. The cable problem is huge, and the engineering challenges are immense. Even if we solve them, the cost would be in the trillions, requiring global cooperation. Meanwhile, rockets are getting cheaper and more reliable thanks to reusable technology. We're already building a more affordable highway to space, one launch at a time. Is the elevator a dead dream? Not at all. It's a vision that pushes us to innovate and reach higher. Maybe we'll never build it exactly as imagined, but the pursuit could lead to breakthroughs we can't predict. For now, rockets are our ride, but we'll keep dreaming of that quiet, elegant elevator to the stars.